Welcome. Today we investigate a lesser-known paradox in relativity called the submarine paradox, or Supplee's paradox, after James Supplee, who introduced it in 1989. Suppose we have a submerged submarine, which is equibuoyant, meaning it will neither sink down nor float up. At first, it is also horizontally stationary with respect to us and the water. Good. Now, what do you suppose should happen when the submarine gets moving? Should anything happen? Well, yes. Because of special relativity, the submarine should Lorentz contract. What does this then mean for buoyancy? Recall Archimedes' principle? It says that the upthrust force is the weight of the displaced water. But now, the submarine is contracted, so there's less water to displace. Therefore, the buoyancy force is smaller and no longer capable of counteracting the pull of gravity. Thus, the moving submarine will sink. Eureka! Right? But now let us rock the boat by considering the co-moving frame of the submarine. In the rest frame of the submarine, the vessel has retained its full length and volume. There should be no reduction in buoyancy then. From the submarine's perspective, Archimedes' force still appears strong enough to balance gravity. So the sub doesn't sink after all? Wait, it gets even worse. In the submarine's frame, the water is moving, and therefore it is the water that is contracted, meaning the water is denser than before. Since the total weight of the displaced water has increased, Archimedes' principle implies that the buoyant force is even stronger than the pull of gravity. In this co-moving frame, then, the submarine will float up. How can that be? Many things are observer-dependent, but a submarine cannot hit the sea bottom in one frame and float to the surface in another. And there you have it, the submarine paradox as promised. Enjoy. Pause and give it a try if you like. Note that gravity plays a central role here. Gravity is part of general relativity, so will this turn out to be an exhausting exercise in metrics and tensors? Luckily, no, unless you want to. We present essentially two solutions. First, we use a trick based on the equivalence principle, which allows us to bypass differential geometry. The second method relies on an important aspect of gravitation, often called gravitomagnetism, for gravity has effects which resemble magnetism in their behavior. Gravitomagnetism provides an exceptionally clean solution into our submarine paradox, which can be understood by anyone knowing just a little bit of electrodynamics. We will not be considering turbulence, drag, or other boring realities in this abstraction of a puzzle. Alright, let's dive in. We assume a flat ocean and a flat sea floor and a uniform gravitational field. This gravitational field pulls down the submarine, which is submerged in the ocean. The submarine has mass m, so the force of gravity is mass times the standard gravity g. On the other hand, the force of buoyancy is trying to lift the submarine up. Archimedes' principle says that the total force is equal to the weight of the displaced water, which is the density of the water, ρ, times the volume of the submarine, v, times g. We assume that initially the buoyant force exactly cancels the gravity. The mass of the submarine must equal the mass of the displaced water. Remember this, we will be using it to make cancellations in future equations. Gravity is awesome, but dealing with it as a space-time curvature can make one feel like a fish out of water. Luckily, we have the equivalence principle, which implies that local effects of gravity are indistinguishable from an accelerating frame. Let us change into a coordinate system where the ground, or seabed, is accelerating up with acceleration g. In such a frame, there is no gravitational field, locally at least. For visualization purposes, we will draw these grid lines, which represent our acceleration, with respect to the original frame. An alternative interpretation, if you prefer, is that space accelerates downward, a viewpoint often called the river model of gravity. Next, what happens to Archimedes' principle in this frame? The equivalence principle ensures that local effects of a uniform gravitational field are indistinguishable from those of an accelerating frame. So, Archimedes' principle must continue to hold in some sense, right? Yet, there is no gravity. So strictly speaking, weight, if understood as a gravitational force, is zero. However, there will be a pressure gradient produced by the accelerating seabed that pushes the water upward. Let us check some tedious details since a proper understanding of this point turns out to be very important. Here we have a box-like water element. Suppose it's being accelerated upward at a rate a. By Newton's second law, the total upward force acting on it must be equal to the inertia of the water element times its acceleration. Assume this force is provided by the difference between the pressure forces acting on the lower and upper faces of the element. Representing the pressure variation with differentials and dividing by the volume of the element, we obtain a familiar expression. Thus, there is a pressure gradient of the same form as in an ordinary gravitational field. This is all that is needed for Archimedes' principle to hold in an extended sense. The force of buoyancy is the mass, or more like inertia, of the displaced water times the acceleration. Note in particular that the buoyancy is proportional to the acceleration of the water, a fact which will be essential later. Also, the density ρ should be thought of as inertial density rather than mass density, since for relativistically moving objects the concepts will be different. Back to the main story. The buoyancy will exert a force on the submarine, which results in a constant acceleration according to Newton's second law. We have thus checked that the relative acceleration of the submarine with respect to the water remains zero, meaning that, in this frame, it is equibuoyant. Smooth sailing so far. Now let the submarine boost to speed v to the right with respect to us. It will contract according to special relativity. Thus, the volume v of the moving submarine will be smaller by the inverse of Lorentz gamma factor. Gamma is a number greater than 1 and gamma inverse is a number less than 1. We shall set the speed of light c to 1, so velocity v will mean fractions of the speed of light. We assume the vertical velocity of the submarine stays non-relativistic. This way only the sideways speeds will affect the gamma factor. For calculations, we will even focus on the instant where the vertical velocity is zero. Our visual illustrations, on the contrary, exhibit exaggerated vertical movements. Moving on. By Archimedes' principle, the buoyancy force will also be reduced by a factor of gamma inverse. Since the upthrust is reduced, buoyancy will not be enough to accelerate the submarine at the same rate as the water. The conclusion is that relative to the water, the vessel will sink. Moreover, consider this. The submarine is moving in this frame, so it has kinetic energy. According to special relativity, more energy means more inertia. In fact, let us have a quick refresher on how Newton's second law is updated in special relativity. Skip ahead to the next timestamp if you're familiar with it. The relativistic momentum is the classical momentum scaled by the gamma factor. The 3 force is defined as the rate of change of momentum. The invariant mass can be taken outside the derivative, after which the product rule separates the right side into 2 pieces both containing acceleration. This relativistic version of F equals ma is complicated, but the relation becomes quite simple when the acceleration is perpendicular to the velocity, which is the case in our submarine paradox. Thus, for transverse acceleration, the object behaves as though its inertia were increased from m to gamma m. This is sometimes called the transverse inertia, or transverse mass. We can continue our relativistic dynamics of the submarine. In all our scenarios, the velocities are always essentially perpendicular to the acceleration. That is why we made the simplifying assumption of non-relativistic vertical velocities. For vertical acceleration of the submarine, then, we get the following. The acceleration due to buoyancy is reduced by gamma inverse squared. The relative acceleration is negative, We confirmed that the buoyancy is unable to keep up with the ocean and seabed, and the sub will sink. Interesting. And makes sense so far. Things take a turn when we step into a frame which is moving to the right with the same velocity as the submarine. First, in this frame, the submarine will have its full length and volume, so the volume of the displaced water is the same as in the equibuoyant starting state. But the water is moving now, so the water molecules are packed more densely due to length contraction. The number density of water molecules is increased by gamma. In the equations, the primed entities refer to values measured in the moving frame. The denser water increases buoyancy, so the buoyant force should be stronger by 1 gamma factor. Since buoyancy has increased, the submarine should be floating up, but we're not done. As before, the dilemma gets worse when we take into account the relativistic inertia. A moving water molecule has more energy and more inertia. So as the water is moving, then a given volume can pack more molecules, each molecule carrying more inertia. Therefore, total density, taken to mean density of inertia, has increased not by 1 gamma, but gamma squared. By our extended Archimedes principle, the buoyancy force is the total inertia times the acceleration. The buoyancy is stronger by gamma squared. That in turn implies that the submarine seems to accelerate faster than the water or the sea floor. Relatively, it floats up, a paradox. It's time to finally resolve this puzzle. It turns out our picture of the co-moving frame is incomplete in 2 ways. First, the left moving water does not actually accelerate up at the original rate g, as it did in the stationary frame. Can you imagine why? The time dilation. Look at the following situation. First, we are in the stationary frame. We have a water molecule which starts from rest at the origin and is under constant acceleration g up. Let's say it moves up by height y during time interval t in this frame. From high school physics, we know that the distance y is equal to 1/2 times g times t squared. To be exact, in special relativity, a trajectory under constant acceleration is a hyperbola, not a parabola. But we're omitting the relativistic effects from the vertical velocities. Let us next view the situation from a frame moving to the right with velocity v. We can simply perform a Lorentz transformation like this, where the prime coordinates refer to the new moving frame. The Lorentz contraction does not affect the transverse direction, so the height in this frame, y prime, equals the original y. For the selected water molecule, the original coordinate x is 0, since the particle is not moving sideways in the original frame. The coordinates of the water molecule in the moving frame are these. From here, we represent the old time t in terms of the new time t prime. We just derived the usual time dilation. A moving clock runs slow. Plug these into the equation of the parabola, and we get a transformed parabola. From this, we can read off the new acceleration, g prime, of the water molecule. It is the original g times gamma inverse squared. Interestingly, the upwards acceleration of the water is reduced in our moving frame. Remember when we emphasized it is the acceleration of the water which creates the pressure gradient and therefore buoyancy? Well, now the acceleration has decreased, and therefore the buoyancy supported by the moving water is reduced by gamma inverse squared. We have 2 competing effects. On one hand, the inertia of moving water has increased by gamma squared. On the other, the time dilation reduces the acceleration by gamma inverse squared. So these 2 effects cancel each other out. Suddenly it seems like the sub is neither sinking nor floating up. This is better, but to resolve the paradox, we need to get the sub sinking. What follows next is the key part of the solution. The ocean floor is not flat in these coordinates. If you've never done Lorentz transformations with accelerating objects, this might come as a surprise, so let's check it mathematically first. In the original stationary coordinates, the upward accelerating ocean floor can be defined using this equation. Height y equals 1/2 times g times t squared. Note that height y does not depend on the x-coordinate since the ocean floor is flat in these coordinates. The seabed is just uniformly rising up. Now we use the inverse Lorentz transformation to replace the original coordinate time t with this expression obtained from the inverse Lorentz transformation. At any fixed time t prime, the dependence of height y prime on the lateral x-coordinate x prime is quadratic. That means the profile of the ocean floor is parabolic in this frame. Conclusion? The buoyant force alone cannot make the submarine sink relative to the ocean floor, but the ocean floor itself, by curving, comes up to meet it, so to speak. Effectively then, the submarine will approach the ocean floor. The sub is sinking. Finally. We can calculate the rate of sinking by studying a point on the seafloor directly below the submarine. In the comoving coordinates, the submarine's x-prime coordinate is always 0. Therefore, the projection of the submarine onto the seabed directly below also has x-prime coordinate 0. By a straightforward substitution, we find that the relative upward acceleration of the seabed right below the submarine is gamma squared times g. Meanwhile, we have seen that the submarine itself is under the original buoyancy and therefore experiences the original acceleration g. Thus, we arrive at this final formula for the sinking rate. That's it. In both frames, the submarine sinks. Paradox resolved. You may have noticed that the relative accelerations obtained in the two frames are not numerically equal. This is not a contradiction, because coordinate acceleration is not invariant under a Lorentz transformation. In fact, they are a double time dilation away from each other. Here we are again, using the assumption that the vertical velocity is non-relativistic, so gamma factor stays constant. Algebraic acrobatics aside, why does changing reference frames turn a flat ocean floor parabolic? It's a consequence of relativity, of simultaneity. Let us demonstrate by starting with the sideways moving line. We switch to sideways movement to reserve vertical dimension for time, as we'll see. Let us first see what happens to a uniformly moving line when we boost forward. In the spacetime diagram, where the vertical axis is time, the word line of the left moving line forms a plane. Initially, our plane of simultaneity is an xy plane. When we perform a Lorentz boost into a forward-moving frame, our own plane of simultaneity tilts. This changes the intersection between our plane of simultaneity and the plane representing the left-moving line. In a sense, this happens because the events further ahead skip ahead in time, and so move further to the left in space. Now, what if a left-moving line was under constant acceleration? Before our boost, the world line, or more like surface of the line, would appear parabolic in spacetime, like this. Let us again boost to a forward-moving frame and thereby tilt our plane of simultaneity. This time, the originally straight intersection deforms into a parabolic shape. The intersection is how we determine the shape of the original line. That is one way to understand how an accelerating flat shape can turn curved under a simple Lorentz boost. Transforming away the gravity was a nice trick, but one might be left wondering, what is really going on under the surface here? How would gravity behave if we do not transform it away? We will next present a viewpoint which, although only an approximation to full general relativity, reveals a valuable insight into the nature of gravity. Let us go back to 1905 and start by quickly reinventing gravity. Shouldn't take long. We have Newton's gravity, we have Maxwell's electrodynamics, and we have the brand new Einstein's special relativity. And we need to make them coexist. Electrodynamics is already compatible with relativity. In fact, electrodynamics was Einstein's main motivation behind special relativity. Newton's gravity, however, acts instantaneously at a distance, which is an absolute no-go according to special relativity. This little kink must be pretty hard to fix, right? Like 10 years of Einstein's life hard? Actually, it's gonna be super easy. Barely an inconvenience at all. Here's a hint. Compare Newton's inverse square law and Coulomb's inverse square law. In electrodynamics, the static Coulomb law blossoms into Maxwell's equations, which are compatible with special relativity. So, perhaps Newton's law can be extended into a similar set of gravitational Maxwell's equations. Compared to Maxwell's equations, there are just a couple of sign changes in front of the sources to account for the fact that in gravity, masses always attract. The force law can also be updated into a Lorentz-type force law. Here, the B field is a new gravitomagnetic field, while G is the usual electric-like gravitational field. These equations would automatically make gravity compatible with special relativity. In particular, it would fix the issue of instantaneous action at a distance. For, as we know from electrodynamics, news about disturbances in the field travels at a finite speed, the speed of light. Such a direct analog of electrodynamics is often called Maxwell heaviside gravity, or a Maxwellian form of gravitomagnetism. Today we know, of course, that general relativity is the more correct theory of gravity, but gravitomagnetism does work as an approximation. The point is that gravitation, even in general relativity, exhibits magnetic-type phenomena. Often the simplest way to understand them is by a comparison with electrodynamics. Let us therefore investigate how gravitomagnetism can shed light on the submarine paradox. More discussion on the gravitomagnetism later. We again set up an equibuoyant submarine at rest with respect to the water. In this frame, the gravity is represented by a vector field G, pointing straight down. There is no gravitomagnetic field B, since there are no moving sources. Then, the submarine boosts to a horizontal speed V, making it contract as before. And as before, the buoyancy force is reduced by 1 gamma. The pull of gravity is stronger by 1 minus gamma inverse times m times g. Okay, let us hop on to the comoving frame. In this frame, the source of gravity, Earth, is moving to the left, meaning there is mass current. Moving sources mean the presence of a gravitomagnetic field B'. What does it look like? If you know your basic magnetostatic, you can venture a guess. A static plane current is flowing to the left. A current acts as a source for the magnetic field B'. So the magnetic field should be pointing sideways, as visualized here. The calculation of a magnetic field for a plane current is easy to calculate with Amperian loops and symmetry. We skip the calculation since we soon get it another way. There's an extra effect due to Lorentz contraction, however. In this frame, the moving source, the Earth, is denser. Therefore, the gravitational field G' it creates is increased by a gamma factor. And by the same token, the current is also greater by 1 gamma factor. Therefore, the density-corrected gravitomagnetic field is stronger. Alternatively, we can skip the analysis of sources and obtain the fields with Lorentz transformations. From electrodynamics, one knows that electric and magnetic fields transform under a Lorentz boost like this. Recall, our speed of light is set to 1. By analogy, the gravitational and gravitomagnetic fields transform similarly. We see that the parallel components are unaffected. In the transverse direction, the fields intensify by gamma, which can be interpreted as field lines becoming denser to the Lorentz contraction. However, the two fields also get mixed depending on the velocity. In our case, the boost V is in the positive x direction, and the original frame gravitomagnetic field B was 0. Substituting these into the transformation equations, we find that in this moving frame, the gravitomagnetic field B' is non-zero. From the transform equations, we can again observe that the strengths of the fields are scaled by gamma, previously interpreted as the sources becoming denser. Now we have the fields. How will they affect our submarine and the water? By direct analogy with electrodynamics, Newton's force law is replaced by a Lorentz-type force law. Here U' is the velocity of the body on which the force acts. A magnetic field only affects moving bodies, so the submarine is unaffected by the non-zero gravitomagnetic field. Therefore, only the increased G field pulls the submarine down, implying the submarine is heavier in this frame. By the same token, you might think the water molecules too must be heavier. Well, stationary molecules would be heavier. The gravitoelectric contribution is indeed increased. The moving molecules, however, feel the magnetic component of the Lorentz force law. The magnetic force will point up in this case. The effect is similar in nature to two parallel current-carrying wires, although the sign convention is different in electromagnetism. The total force on the water molecules remains downward, but it is reduced by gamma inverse. There is one more factor to consider: the density of water molecules. The number density is increased, as before, by 1 gamma. Therefore, even though a single molecule is lighter by gamma inverse, the overall weight of the water displaced by the submarine is unchanged by our Lorentz boost. The buoyant force is therefore unchanged. The total force on the submarine in this moving frame is, as the following calculation shows, negative. The submarine will sink. Numerically, the force in the moving frame is not the same as in the stationary frame. But this is to be expected, since force is tied to acceleration and inertia. In our case, where the acceleration is perpendicular to the velocity, the relation is particularly simple. We already know how the acceleration and inertia change in special relativity. Therefore, we can derive how the force will transform. It all checks out. You might be wondering, why are we selling an explanation in terms of an approximation? Why not go with full general relativity? The first reason is insight. We're looking for a perspective which would offer tools for our thinking. Sometimes it's useful to relax precision, to gain intuition. In our treatment, we've been using its simplest Maxwellian manifestation, but gravitomagnetism as a concept is not only an approximation. It's a more general feature of gravity. For example, in GR, the evolution of the test particle is described by the geodesic equation. In a frame where the stationary metric is explicitly time-independent, the line element can be written in this form. If we then define a gravitational field G and the gravitomagnetic field B with these definitions, the projected geodesic equation takes a familiar shape. V denotes the velocity of the test particle as measured by the stationary observer. The tile on top of the nabla operator indicates that the operation is taken with respect to the three-dimensional spatial metric h. The left side of the force equation is curved space analog of acceleration, that is, the spatial covariant derivative of u along the trajectory, including the Christoffel symbols of h. Let us moreover use the time measured by the stationary observers. We may define the effective inertial three-force measured by the stationary observers as this. The geodesic motion of a stationary spacetime can be represented with a force law that looks a lot like the Lorentz force. Note that this is not a weak field approximation. You could apply it to a rotating black hole, for example. Even though gravity is not fundamentally a vector field, often one can reformulate a problem in terms of gravitomagnetic force fields. Unlike what is often presented in textbook narratives, it was not especially difficult to construct candidate theories of gravity compatible with special relativity. So why was Einstein not satisfied with them? Because Einstein insisted upon incorporating the principle of equivalence. Today, the equivalence principle may seem like a compelling requirement, but for most physicists at the time, it was not clear that one should add such an extra criterion to the theory. Einstein was almost alone with this conviction. The Maxwellian theory of gravity does not comply with the equivalence principle. Therefore, it is not the complete story. But this does not mean that gravitomagnetism should be forgotten. General relativity predicts many phenomena, like frame dragging, that are fittingly described as magnetic in nature. Gravitomagnetism is very accessible for anyone with some skills in electromagnetism. It provides wonderful shortcuts to many of the more exotic features of gravity, without the machinery of differential geometry. Consider gravitational waves, for example. Simply by analogy with electromagnetic waves, the existence of gravitational waves seems rather natural. Gravitomagnetism is a fun and underrated framework that allows one to transport a lot of practical knowledge from electrodynamics into gravity, free of charge. Pun intended. A technical note. In the literature, the word gravitomagnetism can refer to a wide class of theories. These different formalisms are closely related, but they're not all the same theory. Our first solution used the equivalence principle. We transformed gravity away by shifting into a frame where the ground was accelerating up. This solution allowed us to steer clear of the maelstrom of tensor calculations. As a bonus, we saw how an accelerating plane can bend when switching to another inertial frame. The second solution turned out to be a teaser into gravitomagnetism. We proposed that gravity could be analogous to Maxwell's electrodynamics. From there, we were easily able to solve the problem by leveraging our knowledge about electrostatics and magnetostatics. Let us mention that we know of at least 2 more ways to resolve the paradox, with the full formalism of general relativity and with the kinematics of pressure at the microscopic scale. References to both approaches can be found in the description. And lastly, let us mention that in this video we invented gravitomagnetism simply by making a naive guess. That guess is more educated than we had time to argue. Therefore, gravitomagnetism deserves a future video of its own. Stay tuned. Thanks again for watching and listening. I really hope you enjoyed the video, and have a great day or have a good night. See ya.